Okay, our next speaker is Dr. James Allen. He's a senior research associate in biochemistry at the University of Nebraska-Lincoln, and I believe he's going to talk about green algae for treating nitrate.
Thank you. Thank you, everyone. Good morning. My name is James Allen. I'm a research assistant professor now. We're hearing it, right? Yeah, good. So what I am going to talk about today is our nascent kind of little baby approach to a company. We're trying to fit this space under the cost of reverse osmosis treatment. So essentially, what that is what the company is trying to do, is to produce a lower cost biological based system for treating water for municipalities for drinking water. And that's it's a regulatory way. That's a problematic thing, but that's still our goal at the moment, and we're not completely sure where it's going to go right now, but that's what our goal is. So I'm going to be talking about this groundwater nitrate remediation in Nebraska by algal sequestration. What I mean by that is algal growth. So what we're producing is a photobioreactor system for that. Okay, so a little bit about me. I have been in kind of the algae biotech space for about 9 years. I started out with these large DOE and NSF EPSCoR programs in the Beetle Center at UNL. And basically, this is sort of an introduction to why we would use algae for anything, really. Algae has come up many times over the decades for biotechnology purposes, for different reasons, because it's a very tempting system because it grows very quickly. For one thing, we know that it can produce fuel, and it will in the future, believe it or not, be an important aspect to our fuel economy, because it is a carbon neutral drop-in fuel that is one that we can use immediately. So it's just a question of cost. So at this point, I think it's still about $20 per gallon by estimate for the cost of that fuel, but we're working on it. So the problem is that it only produces oil during abiotic stress. So you can see these two. These are confocal images. On the left is a normal algae cell growing happily, and then this is the nitrogen-stressed algae cell. And you can see these are stained lipid droplets here. These round red things are stained. So they do produce a lot of oil. They do produce about 20% by weight at the end of it. It takes a while, but they do that. The other aspects of it is that they tolerate wastewater, so they don't use a lot of land, especially if you're using photobioreactor systems. And they don't have, in that sense, they don't have a lot of impact on our food system like biofuels type of plant production systems would have an aspect of the land production that would impact food production eventually. And that's, as all of you know, that's a problem. So we actually recently demonstrated that you can use temperature as well. So this is a kind of a breakthrough for us. It's in a very tight band of temperatures, but this is something that we're looking at. One of the reasons why we're doing things in photobioreactors as well. So this is the species that does that here. Okay. The nitrate aspects and the health aspects and everything, I think, have been pretty well covered at this point by people that are a lot more qualified than I am to do it. But I think that this picture illustrates pretty nicely what happened to nitrogen and why we're talking about it now. The Haber-Bosch process in the early 20th century, produced the ability for us to put a bunch of nitrate on and, increase the population of the world by, from, half a billion to, 7 billion now. So the problem is that, plants don't absorb as much. It's debatable how much they actually absorb. I'm sure it changes in different soils. But the problem is that, we talk about 120 pounds of nitrogen that's added to fields. 1 pound of nitrogen, nitrate nitrogen added to fields will essentially contaminate, if you want to use that word, 12,000 gallons of water if it reaches the groundwater. So we have a stable increase in the United States still. And the point that I have with this worldwide food demand is that we're not going to stop using it. It's going to increase. We're going to have to increase the amount of land that we're using and, steadily improve on things. So it's not going away. And, we love this map in the conference. My point really for this, I won't go over this again, is that on a national level, a slightly different way of looking at this map from the biotechnology sort of aspect. Everything on this map essentially is here in Nebraska. So it's like 62% of the pixels on this are in Nebraska. It's a huge amount of the responsibility, let's put it that way. In other words, my point is that I don't think that anybody from the outside of Nebraska is going to come in and try to solve this problem that municipalities are having with their high nitrate water. I don't think they're going to try to solve that for us. So I don't think that companies are going to come in and solve that for us. That's one of the reasons why we decided to try to do it, is because we feel it's important for us to innovate out of this problem, as well as deal with it from the point source aspect. And we do have 70 years of nitrate adsorption in the Vestal zone, so that's not going anywhere. Well, I mean, it's going into the groundwater, but the groundwater problem is not really going anywhere, as we all well know by this point. So, I'm not going to go over this. I mean, there was just a whole big talk about this, but I want to re-emphasize the fact that nitrates are, they're good and bad. They could be good or bad, so they could affect, positively affect your cardiovascular system if they're pushed towards nitric oxide, if they're pushed towards these nitrosamines, if indeed that's what's happening, then there's a good possibility that they're doing bad things to you. So, there's a lot, nitrates are in our food too. So there's a lot of vegetables that have high nitrates in them. It's not like they're bad for you. They just have to be in association with compounds that push them more towards the nitric oxide and less towards oxidation reactions, like antioxidants or whatever. So that's really pretty much all I have to say about that. So what we really need, and this is what I'm trying to emphasize, is we need a twofold approach. What we believe we need is a twofold approach. One of those approaches, which is improving the nitrogen use efficiency, I think you guys have that covered. It sounds like that's the main focus of this conference, and that's great. But I think we also need to have active and mostly, so from our perspective, cost-effective ways of mitigating that nitrate before it goes into the groundwater, before it goes into drinking water, for municipalities or maybe even private well owners, if they are in clustered large enough amounts, maybe. So what we're doing is we're trying to develop this kind of an engineering system to try to sort of kind of short circuit this this algal growth that we see in nature, what we think is that reverse osmosis systems are not necessarily too expensive for the producers, but too expensive for many people to implement. And we've heard that many times over the last couple of days as well. And 1 pound of algae can effectively take out nitrate from about 600 gallons of water. And so once again, what I'm talking about, remediation with algae, is actually just using the algae growing the algae on this water. That's essentially what I'm talking about. I mean, the well water actually grows algae quite nicely. Oftentimes you have to add phosphate to it, but it does actually grow really to very high densities just off of well water, and removes that nitrogen pretty well completely. And the reason for it is because you're just making proteins. And, just to be clear, that's what I'm talking about. Although you can, through some manipulations of the abiotic circumstances, you can get the algae to actually pick up more nitrogen. This is what we found than is necessary for the algae. So, this is what we're talking about. The concept is to really short circuit this issue that we already have with algae. So essentially, grow just like Tiffany, Dr. Messer was saying, if you can catch it before it actually creates the issue, if you can somehow sequester it before it gets out in the environment or before it becomes an issue in the environment, then we will mitigate all these economic costs and everybody will be rich and happy. So it's a lot of money that we're talking about. So economic losses in the U.S. from freshwater algae, this is from, not being able to drink the water or just like, having closed beaches or whatever, is roughly $2.2 billion annually for the U.S. This is not a small amount of money. If we can approach this problem, then we can basically help everybody out, really. So the question is, can it be grown on this water before we have these negative downstream effects? This is just a brief introduction to my design approach, which is, it's more important than it looks like it is. I have an iterative approach. So we're designing these systems in a way that's unusual. It's a little bit novel. One of the things that occurs with algae, so there's been, if anybody knows about anything about this space, there have been a lot of algae companies that have come and gone. So it's not unusual for an algae company to start up and then be done pretty quickly. It's a difficult area to work in. One of the problems that you find is that when you develop everything in a laboratory and you try to take it out into the field, that's when things don't work. It doesn't grow as well, it has pathogens or whatever. So there are two approaches that I have, that I think are lacking in algae, in general, in algae research or implementation, which are this iterative approach to using the biology to constrain the engineering side of it, or the design side of it. In other words, design the photobioreactor to suit a particular strain, and then choose the strain based on how well it works in a bioreactor system in that water. So and this is why we have to do it here in Nebraska on the well water, specifically, because it makes a big difference with algae. But we also have to, so this is what we're doing next. So this is the next step. What we're doing is taking the stuff out into the field, into greenhouse settings with the well water, because we need to actually encounter the problems during the design phase in order to overcome those problems. And basically weather is a big problem, temperature is a big problem, and then the hardness of the water is somewhat of an issue, but it's not a deal breaker. So you have all of these for the algae itself. You have all these. So you have all these different parameters that we're looking at, and there are also these other parameters that you have to worry about, which are the economic parameters. So you have to worry about the cost of things, which, but long story short, if we can actually, if we can get the costs down, which is our main goal, essentially, then what we can do is sell the algae and, essentially make our money like that and clean the water. That's the goal. So we want to make enough algae to sell it. There's markets coming out in algae. The fact that it's well water and not wastewater is important to us because we can actually make nutraceuticals or things like that. So really the main goal, we know that it works. I mean, there are other companies that do this photobioreactor stuff with wastewater specifically. This is the first company this is the first approach to try to do this with groundwaters. But with wastewaters, there are several companies out there that are trying to get into the space. So we know it works. It's just a matter of the cost of it. You know, so that's the major innovation for me is the cost. The people of Nebraska, in our estimation so far, do not care about how the system looks. They don't care if it's slick. They just, if it works, it doesn't matter. All the bells and whistles and how it looks is not important. So we are trying to reduce the cost as much as we can by innovating. We want to be able to produce clean water on a site year-round. And so in order to do this, we have to determine these the real world, the production rates and the energy costs associated with it. And so that's what we're doing. Right now, we actually have a codified partnership with a city called Hickman. I don't know if anybody's been there. They got a lot of good things going on there, I can tell you. They've got a lot of people moving there, and it's really dynamic. It's still a very small city, but they have a 30 ppm well that's like right next to their water purifiers. It's great for us, and they're on board, and it's only about 20 minutes from the lab, so that's great too. So this is our sort of planned progression. We have this. We've had this 200 liter lab reactor, and so now we've moved into a different space. We're at the Nebraska Innovation Campus. If anybody's been there, you can possibly come by. I don't know. Depends on what reactors are up at the time. And so the next step is we want to do this 2,000 liter greenhouse step to really get that kind of data, and then move it up incrementally by factors of 10. So it's I think it's so this is the system. The details on the data that we have so far, well, that I can show you on this system. So what we are using right now is this it's a helical glass system. So it's a bunch of tubes that are just sort of in a big circle essentially. And this is from a batch system, so we will, once we scale it up, it will be continuous flow system. But for right now, it is and continuous flow will take about 200,000 liters for continuous flow for it to reduce the nitrate by 10 ppm over the course of a day. We get really good, consistent results off it. I mean, like we expected. It was bumpy to get the system up, but we did expect to get good results eventually. And I mean, the algae takes nitrate out of the water. I mean, I shouldn't discount the fact that we've been innovating on this. I mean, we have actually increased the amount of nitrate that we're taking out of the water and the growth by about 4-fold over the course of this last 6 months or so. So we've done really well. And we can produce, so I put this in terms that are, so about a quarter pound of algae per gallon per year. So that was my best approach at something relatable. Or 80 grams a day of wet laid algae if you prefer that. So what I want to emphasize with this is, one thing about it is that this Tetradesmus obliquus that we have sort of landed on with this system, this organism is an example of sort of the iterative way of doing things. So the reason why we picked it was both growth rates and also because it doesn't form films as much as other algae that we've seen. So we have a lot less cleaning issues with this algae than we've had with those. So it really reduces the maintenance of it. And then we were able to go through and with the system really optimize the system for its growth. So that's what I was talking about with that kind of thing. So the only other thing I want to emphasize is that, one of the questions that I get a lot is the scale of this thing. So this is not very big. 220 liters is only about 58 gallons. We're talking about putting in like 580 gallons, and people ask, well, how much is that per day? In Hickman, we're still going to be not at a scale that we can do continuous. So we're going to be in a batch mode, meaning that we have water and we circulate it through for a period of time, about a week. So that's the rate. It's about 1 week for that 560 gallons or whatever it is. So the point is it's not really, so we're not producing a system for Hickman at the moment, right? We're actually producing a model essentially, so that we can implement those numbers into a mathematical program. So that's all. I'm out of time anyways.